All right, let's get into it. How's everybody doing out there? I'm not gonna have it here. So hope everybody's doing okay. So everybody's left the room, so just talk to myself now. Except for so, anyways, I don't know. You excited for quarantine or?
My job is basically receiving, no matter the situation, I have to still work. So
I see that. What kind of jobs that?
I look at groceries.
Essential staff. Okay.
It's spinning all there, like.
I bet. No toilet paper anywhere?
No,
It's crazy.
still another public washings too.
Wow. It's wild. I keep seeing posts on Reddit where like people are like catching people selling toilet paper like $60 a roll.
Yeah.
Okay, so we're getting to the most important part. We got a couple more things to talk about that affect rates, but then we will actually get into what are probably the two coolest sections of this booklet. 2 units. I see I got one more, so that's great. There we go. Oh, there's somebody in the room at least. So, a couple people in the room. That's great. All right, so yesterday we talked about some of the factors that affect chemical rate. So let's just quickly back up. In terms of the nature of reactants, we have a couple of factors. We have the bond type. So a weaker bond type is going to have an easier time reacting. It's a little difficult to compare rates of reaction. I do find that this section is simplifying a pretty complicated concept, but I think we can. There's still something something valid about what they're saying in this section. But even yesterday, me and the other chem teacher were talking about how we need to really sit down and work our way through this booklet and this particular section of the booklet. See if you can get a little massage and get smoothed out. So weaker bond types typically can have a faster reaction. So if we compare covalent and ionic bonds, we can think of them as covalent bonds being quicker to react. Generally, this sort of argument is based on the idea of the activation energy. So if it's a weaker bond, then the activation energy is lower. If it's a stronger bond, the activation energy is higher because you have to break the bond in order to form new bonds. So that's sort of where this whole concept is coming from. So that's why we can think about some van der Waals chemical reactions. So it's not particularly a chemical; it's more of a physical reaction. But pencil lead is a great example of a van der Waals reaction. With a simple application of some friction, you can rip all of the graphite sheets off of each other, which are held together by van der Waals forces. So that graphite at the end of your pencil, that's billions and billions and moles and moles of sheets of graphene, which is a very wide flat molecule, and they're layered on top of each other. And when you simply apply some friction, you can break those van der Waals forces. It's not really a chemical bond in a way, so it's kind of it's a bond, but that interaction can be broken very easily. A little bit, even sometimes you can rub your finger on a pencil and you'll get the pencil lead on your finger, so it's very soft. So those van der Waals forces can be very weak. Waxes are held together by van der Waals forces, oils, other things. If you get enough van der Waals forces, you can get some decently strong holding. Tape also works on van der Waals forces, but still, like tape being stuck to something is still easier to remove than it is to blow up salt, or to melt salt. Right, it's melting a salt. Depending on salt, you're looking at 800 degrees for sodium chloride. You're looking at 1,000 degrees for some of the oxides. Okay, when comparing the reactions with similar bonds, the more bonds that must be broken, the slower reaction. In the next section, we're going to talk about reaction mechanisms. Every single, in the reaction mechanism, we approximate that one bond breaks at a time. So if you're only breaking one bond at a time, the more bonds you have, the longer it takes. It also makes it more, the other factor that you're getting here is you're getting the factor of, orientation. Orientation is a really important part here. So I actually want to put a little note on that. Let's make this, what color do you want to use today? Black.
Sorry, I clicked the notification and it's just your live.
Oh, I see.
I didn't read it. I was just like, oh, what's this?
Extra bond breaking requires even more orientation. Yeah, so if you have extra bonds, then that's probably going to require some even trickier orientations. Remember that for a collision to be successful, you need it to be with the correct direction and energy. So. All right, get into this next section. Now I will try to go back during the break and make some more sort of narrower videos that I kind of go through these subjects a little faster or a little bit more carefully, not carefully, but more comparatively maybe. Try to cut out some of this so that when you go back, you don't have to watch an hour-long stream to learn one lesson. But that will require me finding time, which is also going to be a problem. Okay, if they have similar bonds and similar number of bonds, then the state is important. So high energy states like gases and plasmas, they have a much higher rate of reaction. They also typically have higher kinetic energy. So they're making more collisions. You're getting more collisions. You're also getting more. You're getting more collisions, you're having higher energy collisions, so the chance of reacting is faster. This is assuming that you have the same amount of stuff. We're just reviewing from yesterday, so we're on 27 right now. If we have higher temperatures, then similar reactions at different temperatures, we typically expect the higher the temperature, the faster the rate. More, again, all sorts of arguments there. Concentration, higher rates. And then we ended yesterday with talking about catalysts. So catalysts reduce the amount of activation energy requirements. They don't change the products, they just change, and they don't change the enthalpy change. So they only change the rate of reaction. Lowering the activation energy of a reaction increases the number of particles with enough energy to move and to produce an effective collision, as shown by the kinetic energy distribution above. I did a potential energy distribution. I apologize. Let's make a kinetic energy distribution. Okay, so we can do this. We can do it again. So if this was a kinetic energy distribution, so kinetic energy. Oh no, wait. Yes, that's right. Okay, and then this is number of particles. Then at a given temperature, you have something that looks like this. I believe there's a nice video on Classroom that is like, there's a video entirely about this. I think it's the Higgs boson distribution. I signed it yesterday. If you're looking for something to keep you busy, I know everybody's gonna be so bored during the break. And if we have our original activation energy, so this is our activation energy cutoff, so only these particles here are able to react. Then when you apply the catalyst, what you're essentially doing is reducing that energy barrier cost. So we can call this like energy of the cat. So with the energy of the catalyst, you get this additional boost here of these little friends. So that's many more particles that are reacting, so it's a huge benefit to the reaction. Excellent. All right. Hey, we're up to 3 people on the stream. Welcome. If you want to sign in, send me a message. So tell me who's there. Lets me know who's listening. Enzymes are a very common example of these. So enzymes are a huge deal in biochemistry. So if you have interest in biochemistry, then you'll learn a lot about enzymes. In the case of an enzyme, we call the thing that an enzyme reacts, the substrate that reacts with is called the substrate. So the enzyme and the substrate will join together. They'll make what's known as an enzyme substrate complex, and then they'll break apart and something will pop out. And this will be the product. So there's a lot of examples of this that you might encounter in your bio class. I know when I taught Bio 30, we often drew a sort of a little doodle like this, where this is our enzyme. And then we might have like 2 little substrate molecules. So maybe like a sugar. And then they form together. These little substrates go inside. So here's our complex. And then while they're in the complex, something happens. And then they separate again. And when they separate, the sugars are not sugars anymore. There's something else. Maybe a starch. So an example might be a starch, or a complex sugar, something like that. So that's one of the ways that plants will make cellulose and other starchy products. Is they make smaller molecules in their cells, and then those small molecules get stuck into enzymes, and then the enzyme puts out a joined molecule. Soon in my bio class, I'll talk about DNA. DNA has a whole bunch of enzymes involved in reproduction of DNA. So you'll have a DNA polymerase as an enzyme. It can lock onto a DNA strand. The DNA strand works as the substrate there, and then the product is a second strand of DNA that gets formed. So that process, although it's possible to happen without the DNA, or without the DNA polymerase, it will definitely not happen at a fast enough rate that we would be able to reproduce cells. Too slow and too random. Your body actually controls a lot of your body's functions by controlling enzymes. So for example, you can control insulin, and you can control glycogen, and those glycogen, which forms glycogen. So controlling the amount of insulin and glycogen in your blood allows your cells to control how much sugar they have inside of them and how much sugar is in your blood. Poor insulin control is also known as diabetes, right? It's a condition you can be born with or you can develop later in life, is the inability to control an enzyme concentration in your blood, or to become insensitive to insulin, which is another problem, which is type 1 diabetes, I think. Child onset diabetes is the one where your body is insensitive to the enzyme. So the enzyme doesn't function for you. All right, so pressure change is another factor that we might have to consider. So especially in gas systems, the pressure is incredibly important in terms of chemical reaction. So pressure here is the force of particles upon the walls of their container. If the number of particles in the container increases without changing the volume, the pressure increases. So one way to think about this is to imagine your container like so, and or what's a great example is balloons. So with a balloon, right, you might have a balloon and it's got like a dark color to it, right, like this. But if you squeeze that balloon, right, if you squeeze the balloon, so that like, it's a little, I don't know, squeeze the balloon. Can't draw that. So that the, there's a little tiny bit held up. You're probably going to notice that the balloon just becomes like a very light color, and that's because the plastic's all super stretched out, right? So that super stretched out plastic, it's stretching out because there's more force on that plastic, right? The plastic in its natural state is that like sort of darker color where all the plastic molecules are side by side. But then when you push harder on them, the plastic molecules get spread out and there's more light that passes through them and it gets lighter. So that means there is more force when you squeeze on the balloon. You're not pushing any force on it, right? You're forcing the air, but you're actually not pushing any of the rubber that's sticking out. The rubber that's being pushed is being pushed by the air molecules inside. So the air molecules inside are exerting force on the plastic because you reduced their volume. This is where I need a balloon demonstration. When in doubt, a glove will work, I guess. Tiger.
I'm pretty sure there's.
I'm sure there's balloons in the background. Feels weird to leave the string by itself.
That's
Walk away too
takes
far.
some.
It's all jokes from a distance. So right, we have our balloon, and you guys, you all know that what's gonna happen. But this balloon, this finger, right, in its natural state, the natural amount of force inside this balloon is pushing the finger only a little bit. Of course, if we reduce the volume of the balloon, we pop it. So that's also example of force, right? The balloon wasn't popped before, but when I start to try to reduce the volume, the pressure inside goes up, the amount of force inside goes up. Okay. So, think about this. Force is kind of energy, right? It's a kinetic energy, and so, or it's a kinetic energy over an area. So this implies that the more you squeeze, the more force some of those particles have. It might not be moving faster, but the more chances those particles have of hitting each other. So whenever we add more product or reactants to the container, then we'll see a change in rate. If we increase or decrease the volume, then we'll have a change in rate. And even if we add an inert or unreactive gas, we might change the rate. So if adding more particles increases pressure, the concentration increases, causing an increased rate. If removing reactant reduces the pressure, then the rate decreases due to decreased concentration. Wish there was a better way of saying that. Okay. So adding more product or reactant particles. Adding more particles increases pressure. The concentration increases, causing an increased rate. Okay, so I think that's probably pretty straightforward. So increasing concentration, increase rate. So this also implies that increasing pressure increases rate. So if increasing pressure increases rate, then as you'll see on the next page, if we decrease the volume, you increase pressure. So you actually we don't need to add more stuff to increase the concentration for gas reactions. You only need to decrease the volume. Decreasing volume equals increasing pressure, which equals increasing rate. If you really want to think about it, the only thing we've really been discussing is concentration, because all of this is just another way of saying increasing concentration. So in a way, we don't have to think about it as being a special thing. It's not really a special feature of gases. It's more a feature of the concentration rule again. And the idea that gases, because they're compressible, they have other ways of making their concentration higher easier. Unfortunately, with dissolving some salt in water, we can't just crank down on our water container and make the salt concentration higher, because water molecules aren't compressible in the liquid form. In the gas form, we're able to compress quite a bit, but liquid water, not particularly compressible, not in a way that could increase the concentration.
Decreasing the volume increases the pressure?
Decreasing the volume increases the pressure, yes.
With gases.
With gases. Okay. This is why if I just squeeze the balloon and it popped, so that's why it pops, is because I'm increasing the pressure in the inside of that balloon. And increasing the amount of force, increasing the number of times the particles are colliding. Because they're colliding so much, they're more likely to collide with the side of the rubber balloon, and so the balloon is more likely to pop. You can see a little diagram of this idea here. So in this example, remember that concentration is calculated by the number of particles divided by the volume. So in this example here, we can think of this as volume equals 1. If we said this was volume equals, half, and volume equals, what is that, a third? Let's just call it a quarter so it's easier. Oh, it's definitely a third. Okay, so say volume is 2/3 and volume is 1/3. So in this example, we can think about that initially the concentration will be equal to the number of particles, 1, 2, 3, 4. So we have 4 orange particles divided by 1. Here we're going to have 4 orange particles divided by 2/3, so 0.66. Here we have 4 orange particles divided by 0.33. And if we had to get a calculator out and do a little calculation, 4 divided by 1, of course, is 4. So our concentration here is 4. 4 divided by 0.66 is 6. And 4 divided by 0.33 is 12. Ask me how that works. So we can see that the concentration, the relative concentration has increased by quite a bit by decreasing the size of the container. So the only thing that's changed is the size of the container. We haven't added more particles, but the concentration, because concentration is number over volume, has increased. This is a trick we can't do in liquids, we can't do in solids. Not really. Maybe there's, probably without except for the rare examples that maybe exist. Most gases and most liquids and solids are not compressible enough to be reactive that way. Not sure if you can even do it in plasmas. Plasmas are hard enough to work with. Okay, the final piece, I believe this is the last one, isn't it? Yes, is the surface area. So this is all about the orientation again. So orientation here it affects surface area a lot, because when the particles are very large, then only the outside surface area is available. So only the outside surface area is available for those correct orientation collisions. Remember, each collision must come with the correct amount of energy and the correct orientation. So if you have a big chunk of chemical, then these ones on the inside, they can't even react. Right? These ones inside here, there's no way you can get the correct orientation with those particles, because those particles can't even make a collision. We need a collision, we need it to have the correct orientation, and we need it to have the correct energy. But right now, these particles are going to bounce off the edges of the molecule. So until these edge molecules react, the inner molecules will not be able to react. And that'll carry forward. So we're going to be waiting for a chemical reaction here, and then a chemical reaction, and then a chemical reaction, and then a chemical reaction. So it'll be very stepwise. Over here, where they broke up the large particles into a powder, we'll see that the reactions are much more violent, or much faster, because the particle size is much smaller, and then the particles can get in there into the different edges, have more access to the molecules. The closer you can get to having your sample prepared ahead of time as being atomic, or molecular, trying to grind it down to the point where you have very fine particles, the finer your particles can be, the quicker your reaction will happen. And the more homogeneous the reaction will be as well. So when we were making glass, we would often we would have a mortar and pestle, and we'd actually grind glass before we put it in the oven. Even though we're heating it up to 1,000, 1,500 degrees, we still would grind it up ahead of time, mix it a little bit by hand even, put it into the crucible, weigh it, and then put it into the oven. And if you didn't grind it up really nicely, you would actually get little pockets of glass or you get pockets of crystal in your glass, and that was not what you wanted. It was bad. You wanted pure glass. Now there's actually one missing, which is one we do in the lab, and that is stirring or mechanical action. Mechanical action can be used in a similar explanation as this last one about increasing the number of correct orientation collisions. If you just stir the thing while the reaction's happening, you'll also increase that reaction rate. So let's put in mechanical action. A lot of space here. Oh wait, I can add a page. You guys can't, but that's your problem. There we go. Why am I goofing around here? Okay. So let's do a little doodle here. So if you have all your powder sort of sitting on the bottom like so, then you have your molecules have to bounce off of can only hit the edges. If we take the same container and stir it up, now suddenly particles can come at things from any angle they want. So mechanical stirrers and mechanical stir bars are really, really common in chemistry. Almost every chemical lab has will have your hot plate, and underneath the hot plate is a mechanical stirrer, which has you put a little magnet bar inside your solution. You turn on the stirrer, and the magnet bar spins in its place. We have one in this school. It's over there, and it works really well. But it's almost an essential. It's essential lab equipment. There's so many different chemical reactions. You'd sit there. You would be there all day and beyond, waiting for that chemical reaction to happen if you weren't stirring it, because it just would take forever. And in fact, sometimes it might not even happen. Like something like if I'm making like a concentrated starch solution or something, the starch would sit down at the bottom. It would become a big goo. And then it would just sit there, and it would become even more and more gooey until it was just like a piece of plastic sitting at the bottom. It would never stir and never mix. And you do this at home when you're making cakes, right? Or you're making baking. Nobody ever makes baking by just like, okay, add the water and then put it in the oven, right? Like you stir it. If you don't stir it, like you'll have big chunks of baking. Even like powders will stir, right? Like you have like a sifter for your powders, and like if you don't stir them, you get those big baking soda chunks in your food that taste awful. So yeah, so definitely stirring is a huge part of getting a good chemical reaction. Introducing disorder. Entropy. All right, we have some questions here on factors affecting rates. It is only 9:30. I'm wondering if we should try to push through into reaction mechanisms before, and then come back to those and maybe review those on Monday. In Monday's video, I can go through those questions. I'll give you the weekend to kind of work on those. And then the lecture part, at least there's somebody in the room who might ask me a question during it, so I don't just go off on too many tangents. Is that okay with everybody? Okay. This is why I run out of voice by the end of the day. But we're gonna get through this. We're almost done this unit. Okay, so lecture 5. This is reaction mechanisms. This is probably on the edge of your abilities in this course. I think it's on the edge of my abilities, honestly, in terms of doing reaction mechanisms. In certain chemicals, I can probably, like me, with whatever 12 years of chemistry, could maybe do reaction mechanisms for a unique like section of chemistry and do them and probably be right. But most of the time, reaction mechanisms are a huge process to figure out. We're talking about what actually happens to get from these two chemicals to get to this third one. Now, this is a pretty simple system. This one's probably solved, but these things happen instantaneously, almost in like a quantized way, where it's like You have nitrogen monoxide, you have oxygen, and then without shorter than time, you suddenly have nitrogen dioxide. Or shorter than we can measure. There's not the in between transition state is so fast, but we can figure out some things about it as we do more experiments. And with extensive experiments that we're going to talk about in the next section, you can actually kind of get an idea of like, okay, wait, this reaction must be happening in a certain number of steps. You might not be able to figure out what those steps are, but you can certainly figure out how many steps there are. And then that can promote you to go look for answers in other ways. So according to collision theory, for this reaction to occur in one step, all three particles must collide. So if you wanted this to happen all at once in one step, you would have to have all three particles there able to react with the exact correct orientation. So let's think about what that would look like, right? So you're probably looking at, taking, let's do nitrogen will be blue. I'm going to use about that size. Oh, I got to pick a pen here. So my result is I want to get two of these that have two oxygens each, right? Okay, and I'm starting with this, and I have to hit them at the exact same time, all three particles. So this is where, this is probably the first sort of thought experiment you would do if you're a chemist trying to figure this stuff out. So what would you have to do here if I want to get to this point? Can I see a way that I could figure that out? It could be possible. In my mind, I'm kind of looking at, well, that's kind of an oxygen there, right? So maybe, what if this, this oxygen was sandwiched between two nitrogen monoxides? I can use my microscope.
Is it two oxygens, like it's one of the nitrous oxides and pump it into other non-nitrous oxides, that way like one of the nitrous or one of the
Sure, like do it as like a chain, 1, 2, 3. Sure, yeah, you could, but that would be 2 steps. We did want to try to propose a one-step reaction, right? One step would be like, boom. I think like a squeeze makes more sense than a 1, 2. So that sounds to me like 2 steps. I think 2 steps is probably more likely. We're trying to get to a conclusion that 1 step is probably impossible, right? So now you have to think that, okay, well, now the nitrogen monoxides have direction, so they can be sort of rotated around. So you could have 2 that came this way, and that probably not going to work. You could have 1 that came this way and 1 came that way. Well, and that probably not, probably only at like 180 degrees perfectly, or maybe a little bit of tilt, that would be probably the only way that reaction would happen. So we would have to go explore, is this a fast reaction? Is it a slow reaction? If it's a quick reaction, maybe that's it. Maybe that's, or if it's a quick reaction, if it's a quick reaction, it might be in more than 1 step. I don't know. So overall, what I want to kind of get at is that this seems, although possible, it would probably be very difficult to happen. So all I'm gonna do is I'm gonna just move this. So here we've got one sort of very similar to what Nick just suggested, which is to sort of put it in a chain of reactions. So one billiard ball comes in, pops the next one off. Now you've got this free oxygen, and the free oxygen hits the nitrogen monoxide, and we get sort of a 1-2 step. Maybe probably only needs one reactor. And so what we've created is we've created something that doesn't exist in the reactants or the products. This state here of all three of these molecules could be thought of as our transition state. It's probably equally enough. This oxygen could end up, bouncing into something else and then bouncing back and reacting with this nitrogen dioxide and reversing the reaction process. So we're pretty close to a sort of a transition state. This is actually probably an intermediate state. So a transition state would be the point right between this, where the oxygen was just where there's two oxygens attached to that nitrogen monoxide, and now we're in what is called an intermediate state. So this is a reaction intermediate. So reaction intermediates are chemicals created during a chemical reaction, but neither a reactant nor a product. Temporary arrangements of atoms that are created and destroyed during a chemical reaction. So, that one's supposed to be good. Yeah, you should. Oh my god, otherwise. I wasn't that interested in that guy. Just for fun. Oh, okay. It's good, like, part of our stream, I guess. I mean, arguing, but who paid for the Okay. So our chemical, so these are temporary arrangements. So I just feel like next year you get locked up. That's all right. All right, so let's take a look at this one. We just did this already, so we're gonna write out a little sort of we're gonna write out this chemical reaction in a stepwise way now. So the idea would be that something like 2NO plus O2 will first, called step 1, will first form NO2 plus an oxygen. And then we'll take an NO plus that oxygen to form NO2. This will be our step 2. And typically these reactions the intermediate reactions, especially our step 2, is usually the quicker reaction, because in this case we would be left with what is known as a radical, and this radical is not charged. It just has one unpaired electron or two that it's ready to react with. So that reaction is going to be quite quick, because you sort of divided your oxygen molecule in half. You didn't create any charged molecules. You just created neutral molecules that are ready to react. I don't know if I want to move my dot. I'm not confident in my dot, so I'm just going to leave them off. If you need to identify a intermediate, look for something that first shows up on the product side and then shows up again on the reactant side in your mechanism. This is a mechanism. If we add up the mechanism together, we will notice that we get 2 NOs. Oh, I guess I don't need the 2 at the beginning. We get 2 NOs, 1 and 2, and we get plus an O2 plus an oxygen. It gives us 2 NO2s plus another oxygen. And when we add this together, we realize that this is on the left and the right. So they end up crossed up. So our net reaction is just the 2NO plus O2 gives us 2NO2, which is what we had at the beginning. Intermediates can be identified in your reaction mechanism as chemicals that first appear in an early step on the product side, and secondly on the reactants later. Intermediates always cancel out in the final net equation. Now, the very, very, very fun part is that each of those steps has a different rate. And so then we start to find out which of these steps is actually the important one, and it can influence how you proceed in taking on this chemical reaction in the lab. So we are moving to an online delivery mechanism for the next 2 weeks of school, which is this next week and then the break and then the next week after that. So we have 3 weeks in there. I will go, I suppose I won't post during spring break. I don't know, once I get into the rhythm, then I just keep going. I suppose you guys should get a break, although you can get a 3 weeks break. It's just your 3 weeks stuck at home. So for these next online weeks, we have some options. I would like to make it a scheduled stream. I think that will work better for getting people to know that it's a specific time that they should be online. We don't have to necessarily stream every day. We could have sort of, streams scheduled for like Monday, Wednesdays, and Fridays and have assignments on Tuesdays and Thursdays kind of thing or something like that. That could be an option. I suppose you'll have to either talk to me in the chat or talk to me right now before I decide on that.
We can still watch the videos after. Though, right?
Yeah, of course. I leave them up on my site. So it's just I would like to use I'll use a stream if people are interested in being able to chat back. If you're not interested in being able to chat back and you're just going to watch it at your own pace anyways, then another option is I can post videos for each of the lessons and trust that you're going to get into those. And every day I'm going to post something on Classroom. It might be a lesson or it might be an assignment. And then have a scheduled sort of like meeting time through Google Meets. So there's Google Meetup or whatever, and it can also be used to do like an actual sort of conference call. And we don't have to necessarily exchange information. I can just give you a link and you'll be able to join the conference call from your website, from the Classroom. You can turn off the camera.
Okay.
It's pretty straightforward. So that would be another option. So not necessarily having streams, but having like more like those sort of shorter videos I did for the last unit. Try to hit those 15-minute marks and then posting an assignment every day. Whether that assignment's from your booklet or like an assignment that would be in addition. Some of them you might have already. Don't forget to leave without all the materials. Is there anybody have any thoughts on that? Do you want me to do daily streams? Would that be kind of a good like rhythm to your life? Okay, see a good couple of nods there. So maybe that's what I'll continue to do. Because I have the 3 classes, I'll probably do the same schedule and try to get the stream up by 9, and then do the other 2 classes the rest of the day, so that I can kind of be by 1 o'clock. I'll have all my streams up, which is still a full day of streaming. So for me, not so much for you, but it's okay. Yeah. So I'll do that. I'll try to continue to do live streams on YouTube then, and maybe on Fridays we'll schedule or maybe that Thursday or Friday we'll schedule a meeting we'll do a Google Meet on those days instead. So kind of an end of the week kind of discussion that way. And we'll have that sort of conversation. Great. Okay, that's what will happen, and that will be great. So net reactions, we can give us like one little note. You guys know what a net reaction is by now, I hope, but maybe not. So the net reactions represent only the reactants and products in their stoichiometric, which I can't spell.
My pen just went out. I'm sorry. Does anyone have a clue?